Yeah, all right. Then if you're here looking backward and you just look at the electric field vector as it comes past you, in this particular figure, it's rotating clockwise. Now it could be rotating counterclockwise. This is what I call right circular polarization. And the way I sort of remember that is I went out to my shop and I got a drill bit, which is a right-handed helix. And then if you think of the edge of the drill bit, these being electric field vectors at time 0, a little bit later, and so on, then as the drill bit goes into the wood, this vector's pointed here, then a little bit later the drill's deeper, this vector's pointed this way, then this way, and if you were inside the wood looking back at the drill, these arrows would be going around clockwise. So for me, this is a right-handed drill bit, and I call that right-handed circular polarization. That's what Craig Boren uses in his books. The catch is, depending on whose book you read, other people will call this left-handed circular, and about 50% of the people on one side of it and 50% the other way. It depends whether you come from a physics department or a chemistry department or an astronomy department as to how they define right and left. It doesn't matter. You just pick a convention and stick with it in your paper. But when you write the paper, you do need to tell people, my convention is that the electric field vector is rotating clockwise when you look into the beam, or counterclockwise, and just let the reader know. Okay, so as Ken said, the polarized light is described by this 4-element array of numbers, I, Q, U, and V, which is usually called the Stokes vector, although it's not really a vector like pointing in three-dimensional space. It's just an array of 4 numbers here. And to define those, you need to pick a coordinate system that's convenient for your problem. So if you're working in the lab, you might say, let the x-axis be parallel to the bench top, let the y-axis be vertical, and then x cross y would be the direction the light is going. That's what's convenient for a laboratory study. And then people will start calling those not x and y, they may call them the parallel direction and the perpendicular. And you have to keep in mind, oh, well, that's parallel to the bench top and perpendicular to the bench top. Or they may call them horizontal and vertical. Now, it's all fine, you just pick it and you're good to go. The catch is when you read an oceanography paper, they don't have a bench top, they will pick a direction that's parallel to the sea surface and perpendicular to the sea surface. And then they may call parallel, meaning parallel to the plane that's perpendicular to the sea surface. So that's maybe the vertical, but somebody else's parallel may be horizontal. So it's really confusing when you read a paper, and depending on how you define things, you'll get a different Mueller matrix for, quote, a horizontal polarizer versus a vertical polarizer. They'll be a little different. And in a paper, they often don't tell you what coordinate system they picked, but that's what makes it confusing. Okay, enough said. We'll see in a minute that for atmospheric and ocean work, we don't have a bench top. We use these meridional planes, and we'll see more of in a minute, but there's another page on the web book where you can see all the math for those things. Then the thing to remember is when light's propagating through a medium, absorption does not change the state of polarization. It just removes light from the beam. It's scattering that changes the state of polarization. So if you have light coming in here, it's described by some initial Stokes vector, and the light's going in this direction. It hits a particle, it scatters off in some final direction with a new Stokes vector. And as Ken mentioned, you have an initial Stokes vector, then you have to multiply some matrix that tells you how the light is scattered from this direction to that one, so that's through some scattering angle, and then that's going to be a 4x4 matrix that can do things like take unpolarized light, turn it into linear. It can take linear in this direction and turn it into right circular or left circular or whatever. So there's 16 volume scattering functions in here, one of which is for unpolarized scattered to unpolarized. That's what we've been calling the volume scattering function. But there's also a volume scattering function. It would take unpolarized into horizontally polarized, vertically polarized, and so on. So that's just the way the math has to be done at the level of Stokes vectors and polarization. And of course, the scattering angle is still given by this formula we learned on the first day. Okay, so to now that we know enough about polarization, for many decades, radiative transfer theory was kind of pulled out of the air. People just sort of wrote down this equation and it worked and life was good, but there wasn't really a solid connection back to physics. So the whole business of like radiative transfer theory, optical oceanography, kind of got looked down upon by the physicists because we couldn't really justify our connection with hardcore physics. But then this fellow Michael Mischenko has pretty much spent his whole career building that bridge from the radiative transfer equation back to fundamental physics. And so he and a few others have published literally a couple of thousand pages of books and papers working out all the math and all of the physics, and it's all looks to me like it's taken care of now, and no physics professor can have any complaint about anything we're doing. So I want to kind of walk you through just one view graph here, one here, and then how we finally get from the most fundamental physics now down to what Hydrolite is going to solve this afternoon in your labs. So to start with, there's this physical theory called quantum electrodynamics, which is the very fundamental theory of how you describe how light interacts with matter or how charged particles interact. So if you want to scatter one electron off of another one, you do that with QED. And as far as we know, it's an exact theory that actually does explain how the world works with no approximations or simplifications. It's extremely accurate, it's extremely mathematical, and extremely abstract. But to give you an example of its accuracy, here's something called the electron spin G factor, which can be measured to great accuracy, and the plus or minus 28 here means that's the plus or minus on the last two digits here. So here's the measured value of the G factor. Here's the value computed by quantum electrodynamics, all the way out here, and a little bit of error here. That's a comparison of theory and experiment to 1 part in 10 to the 12th. Now, to put that in perspective, measuring the circumference of the Earth to 1 part in 10 to the 12th is the equivalent of measuring the circumference of the Earth to within 4/100ths of a millimeter. It's phenomenal accuracy. And this is considered the most accurate physical theory ever developed. So, because it does give you this 1 part in a trillion accuracy. And its QED is where you play with photons, if you wish. They're considered elementary excitations or oscillation modes of the quantized electromagnetic field. So the photons are the quanta of the electromagnetic field. Well, enough said about that. It's so mathematical that doing a calculation like this may take a year of computer time, and you will have something like 5 or 10,000 10-dimensional integrals to evaluate, which all have to be done numerical, and there's your year of computer time. And the very first calculations, which got you out to about that point, were done by 2 of Feynman's graduate students. And he gave each graduate student the problem to do this calculation for the first term of an infinite series and don't talk to each other. And it took them a year to get the math, programmed up and the computers running, and they got together and the answers were different. And then it took another year to find the bugs in the program till they both got the same answer. So it was 2 years of computer time and 2 PhDs worth just to get you out that far. So that gives you a feeling for the difficulty of it. But if you want to follow up on this someday, read Feynman's book on the QED to have a get started. Okay, bottom line, it's correct, but it's not even the thing that the next step down is that from QED, you can derive what are called Maxwell's equations. And so the process there, QED deals with things photon by photon. And if you have now this fellow here says the classical limit of quantum theory is achieved when the number of photons becomes so large that you basically just almost continue the ocean of photons. And space-time development of a classical electromagnetic wave approximates the behavior of billions and billions of photons. So at that limit, you then get what are called Maxwell's equations, which we don't need to look at, but there's four of them that govern four different variables, such as electric field, electric displacement, magnetic induction, and magnetic field. Okay, so Maxwell's equations now gives light at propagating electric field. And those equations are also perfectly accurate for the classical physics everyday kind of light. So they aren't applicable to oceanography. They're just too complicated to solve. But, so, on the other hand, anything in everyday life, like generating, propagating, detecting radio waves, making electrical power, you have an electric plant running an electric motor, refraction, diffraction, light in our water surfaces, scattering of light, rate of Planck. All of those things are perfectly well described by Maxwell's equations. They do eventually then break down at the atomic scale where you have very high energies, very low temperatures near absolute zero, or when you have some kind of something you're doing that involves individual photons, that's the thing of the theory of optics, then you have to go back and do fancier physics. So even though Maxwell's equations are perfectly accurate for oceanography, they're strictly complicated to solve, and they give us information we don't really care about, which is electric and magnetic fields. If we want to measure irradiances and radiances, and it can get those electric fields, but we can get those to start that we don't have to go through Maxwell's equations. Okay, so back to polarization. When you take Maxwell's equations and do a solution for a propagating plane wave, you eventually then get to the level of Stokes vectors. And the way we resolve the Stokes vectors, remember the Stokes vectors depend on the coordinate system, is we'll have the sea surface here, so that's in the xy plane, is the mean sea surface, and then the light will be going in some direction, and so this vector and the normal to the sea surface, they define a plane, which is called the meridional plane, and that's partially shaded in blue here. So you start out, you say, well, I've got light going in that direction, and so there's a meridian plane, and so I'm going to describe my Stokes vector in that plane. And so I can pick a horizontal and a vertical axis here. So horizontal means it's parallel to the sea surface, and vertical means it's, in this case, normal to the sea surface, or they're perpendicular to the meridian plane, and they're parallel to the meridian plane. And so if I had an electric field vibrating in this direction, that would be vertically polarized light in the meridian plane. Okay. The catch is if the light scatters and it goes off in this direction, then that's a different meridian plane, so I have to translate my Stokes vector from this H prime B prime coordinate system into one for the final plane. So here we see the same thing. Here's the blue is the initial meridian plane. The light scatters and it goes into this direction. Then there's this orange color. That's the final meridian plane. So you have to translate from here to there, and that's done usually as follows. We start out with our initial Stokes vector, and there's this vector, or our matrix C, that transforms into the final vector. And both Now, that's called phase matrix. Usually, you write that as follows. You say, I'm off in the initial meridian plane, but the plane that's shown in red here, it's defined by the initial scattering direction, called the scattering plane. So what you do is you start out and you say, I have a Stokes vector in the initial meridian plane. Then I'm going to translate it into a with another 4x4 matrix into a coordinate system where I have these blue axes that are perpendicular and parallel to the scattering plane. Then in that coordinate system, I'll apply the scattering matrix here, which Ken called the Mueller matrix, but scattering matrix and Mueller matrix are just different words for the same thing. So that's going to do the scattering from here to here, but with the Stokes vector in the scattering plane. Then you end up with the Stokes vector in the scattering plane, and then you have to do another transformation to put the perpendicular parallel to the scattering plane. You need to rotate those to get the parallel and perpendicular to the final meridian plane. So that's the way it's usually done. You can see here a rotation. And so normally go to Maxwell's equation, you go through all of this stuff, you eventually get what's called the vector radiative transfer equation. That one direction here, the integration is over all the other directions. So this is telling you how much light is going in any direction C prime, and it's being scattered from direction C prime into the final direction C. So that's called the path radius term, or phase function term. And then there could be a source of radiance in the water like biofluid. equation.